So much chaos. I appreciate your patience. Obviously, this is not ideal. It's kind of you to bear with me.
What?
Kyle's being very helpful. Everybody laughing doesn't help. So, we will get to the warm-up, I promise. But I'd like to go through the reader, one article at a time, in order. It's important that you have the reader itself and your 7.5, which are the answers to the reader. Double trust rates. No, is that more? One thing I have to warn you is that in previous years, my energy unit reading packet was Gigantor, broken up into 2 assignments. But in anticipation of the block, I've trimmed down my reading packets, knowing that I don't want to lecture for 1.5 hours twice a week. I've kind of cut out content. So everything that's left in your reader is all high-value articles. They're all worth at least 1 or 2 stars, and a few of them are 3-star items. Of course, many of you are like, reader, whatever. And so just as a kindness, I'll give you a heads up that these do show up on my exam Friday, at least a couple of them. And many of these are on here in response to seeing the College Board ask these questions. Given that intro, number 43. 0 stars, interesting visual. We did the Carlotta of the Future a while ago. Congo with the cell phone. We did a Carlotta of the Future a while ago. You might remember in the Carlotta of the Future, I told you nothing worse than gasoline. Maybe soon we can switch to natural gas. Eventually we want to hybrid everything. And if we had cheap sources, sustainable sources of renewable energy, we could eventually end up with hydrogen and electric. Please look up. Number 43 in your reading packet ranks the life cycle carbon output of various transportation methods. Remember what I mean by life cycle output? Cradle to grave, from extraction to disposal, everything in between, the full materials pipeline. So on average, please look up, the black bar that is longest plus the dashed, that's today's conventional gasoline cars. The black bar on top, just the black part, that's if we had just very efficient conventional gasoline cars. 1 bar down, that's natural gas, which you can see is less carbon output from cradle to grave. Then, if we had gasoline hybrids, it's even less. Diesel hybrids, even less. Ethanol hybrids, even less. Plug-in hybrids, given our current electricity sources. And then if we could get hydrogen from all these other sources, look at how much we would shrink the carbon output of those vehicles. I found this to be very interesting. Somebody brought this to a car lot years ago, and I thought, oh great, let's just go with it. So I thought I'd include it for you. You don't have to memorize those numbers. You probably do need to know that ranking, which I think parallels the conversation we had about the car lot of the future, does it not? Anybody want to ask me something about this before I move on? Number 44 gets 2 stars. And number 44 also connects to a study goal earlier in the unit about natural gas extraction and usage. Don't lie to me, how many of you actually read this article? Ouch, that class. Well, maybe you'll remember it from somewhere else. It's possible that the information's in the class anyway. The College Board will often ask you pro-con questions. There's a lot in energy where people are really excited about it, but people are really concerned about it. That's very common in the energy unit. So if you don't already have this in your notes, which I'm guessing you must have copied if you turned it in, you'll want to know pro and con arguments. Reasons that we do want natural gas fracking in the United States of America. Pro. Yes.
Easy to get.
Easy to get, that's true. It is very clean. As a fossil fuel, it's the cleanest. So it's easy to get. It's cleaner than other fossil fuels. It's a good thing you're writing them down. There's the job argument. I always wonder what we mean, because if we made energy from burning babies, that would make jobs at the burning baby plant, right? So I think any new energy source is going to cannibalize the workforce of another one. But sure, there's jobs. Yes?
It doesn't actually pollute groundwater.
Contrary to popular mythology, fracking itself does not directly impact groundwater unless somebody fumbles. Yes? It's important to remember that natural gas is a domestic energy source that's plentiful. We have a lot right here in America.
Lowered energy prices.
And finally, because it's so readily available and so local, it's pretty cost effective. You don't have to spend a ton of money to get it. This would be a relatively cheap energy source. Those are some very compelling arguments. Why would we not want natural gas? Yeah?
It boosts the carbon cycle.
It's more fossil fuels, which is more CO2. Although I gotta point something out. It's more CO2 compared to renewables, but it's less CO2 compared to petroleum.
Yeah.
Yes?
Large toxic chemicals. Your health.
Yeah, there's a lot of toxins in the fracking fluid. So we're messing around with some pretty nasty volumes. Anybody remember why else I was in the fracking conversation?
Isn't it
No. Seems like it. But there is something to do with water. Anybody remember what it has to do with water? Right. Fracking uses tremendous volumes of water, which then must be disposed of. And that's right, that disposal is really sketchy. We're talking tremendous volumes of hazardous material. So reasons that you might not want it, nasty chemistry that we're all kind of nervous about, the potential for accidents is always there, the tremendous water cost, and the disposal of that nasty water. Aren't you glad I'm spending all this time doing your homework for you? Are there any questions about number 44? Okay. Number 45. Again, like I said, there's really no wasting time in this reading packet. Number 45 is 2 stars. Students, what does it mean that our electricity grid is a just-in-time delivery system. Yes.
You can't store it gradually and make it people who need it right then and there.
That's right. Pretty much exactly what Galavan said. We can't store it. We got to be making it right now for all the people who need it right now. It's pretty close to split seconds. Yeah.
You guys really should do this.
Oh, that's kind of the problem. You got to always make more than people are using, so there always is waste.
With this system?
Yeah. Because you can't store it. There's no way for you to just turn it on when you need it at your house. It's being supplied to your house at all times. Think about it. You turn on your washing machine, electricity is available because there was enough electricity available for you to use your washing machine at all times.
Isn't that how our system works now?
That is how it works now. That's exactly what we're saying.
So
We're still talking on the system now.
Oh, if you and where you okay,
Yeah, hey, you're getting ahead of it.
yeah,
I'm still talking about the real system that we've got.
okay.
I use analogy metaphor. I use a metaphor analogy. Imagine if all of your drinking water was just flowing at the house all the time, and when you need it, you just kind of walked up and you drank some out of the faucet, and the rest of the time that you didn't need it, it was just running down the drain. That's our electricity production.
What are we gonna do? That's why we don't want to.
The problem with our energy system now is that there's no storage. So at all given times, we have to make way more than we're using. God forbid there's ever a split second when we're not making enough to keep grandma's life support running. It's one of the reasons there's so much waste in the electric systems. We're always making more than we need just in anticipation that supply might rise, that the demand might rise a little bit. So what if there was a way to store the electricity we're not using? Right now, the power plant, watch me, right now there's a power plant, and then the wires go to your house and her house and her house and his house, and at the end of that wire, unused electricity is pushed into the ground. We get rid of it. But what if we went from the power plant to her house and his house and her house and her house and his house, and then at the end, we had a fancy battery, or at the end, we made hydrogen, or at the end, how about this one? What if we could wind up a flywheel so later on when we need electricity, it spins in the other direction and spins a turbine? Or what if we could, at the end of that wire, pump water uphill into a reservoir so that when we need the electricity, the water comes out of the reservoir and spins a turbine? Number 45, here's why we don't wait. We don't because these things are really expensive and engineering-wise, they have some challenges. Please look up, I did not invent those examples. In number 45, look at me. Batteries, flywheels, compressed air, pumped hydro, and you can add hydrogen. You could add hydrogen. Thank you, Father. Pass this back, please. Pass this back, please. Your middle name is Marie?
What?
Your middle name is Marie. That's my wife's name, Marie. I don't care where you put this, but there's a little concept you're going to need. College Board loves it. You might need it in number 45, or you could put it in assignment 7.3, but everybody needs to know one key concept. These things are opportunistic. We only get these sources of energy when the sun is out, or the wind is blowing, or the ocean's doing the right stuff.
Well,
Yeah.
isn't the ocean always oscillating?
Some of them are more dependable than others, yeah, but even in some parts of the ocean, it gets pretty glassy from time to time. Yeah, that's true. Some times I looked at it, but not in many places. How about this? There's one concept that might make more sense. These are not on demand. Right now, when you go home and you all turn on the air conditioning at 5:30 p.m. in the middle of summer, there's some person whose job it is to sit monitoring the grid and go, yeah, it looks like everybody's turning on the air conditioning. Call the coal burning power plant in Mojave and have them make more electricity because our demand is coming pretty close. And so they keep stepping up the supply as our demand rises. We can't do that with these. It's like, hey, we got a bunch of electricity. Anybody need it? They're like, oh crap, cloud's coming. We got to turn on the natural gas again. This is what I mean. Please look up. These are all opportunistic forms of electricity. We can get free electricity sometimes, but not when we need it. So the funny thing is, if we do all of this stuff at once, we still need the exact same fossil fuel power plants. We'll use them a little less, but we still need them. Because there's going to be some time when there's no wind and no sunlight or whatever.
Yeah, but can you cut back a lot on like how much you use the fossil fuel plants if you're using a lot of those methods?
That's true, but the funny thing is, the only power plant that you know you could do with independently is the fossil fuel ones. Imagine that you're the guy who runs the grid. Do you want to build 20 power plants to supply energy to everybody, or just 5? If you ran all of these, you still need the fossil fuel ones. So you might as well use them up and not bother with these.
More environmentally friendly, right?
Until environmentally friendly saves you money, why would anybody do that? The economics don't make sense. This is a free market economy. This is exactly the problem that we've got. If we could store these, then we can get away from a fossil fuel grid. That's why storage is such a big whoop. Because renewables on their own are pointless. Renewables plus storage, now we can get rid of the fossil fuel power plants. So the problem with these is, like number 45 says, all these alternatives are actually like really expensive. And engineering wise, they're not very usable. So it's just cheaper right now to do fossil fuels than other renewables. You know, like per kilowatt, these are pretty cheap. But as far as a grid investment, they're not really worth it. Yeah.
It's really like that big a problem for government.
That's a really interesting question. Anything I say would be politically biased, but the government doesn't very much subsidize most of these except at the state level. California subsidizes these because California is trying really hard to get away from carbon emissions. California is trying to be like a cleaner economy. At the federal level, we don't really subsidize those very much. They're not very powerful lobbies yet. We're starting to. Little bits here and there, grants and occasional experiment funds and stuff like that. Anybody want to ask me any questions about number 45? You understand what I mean about the need for storage? Oh, by the way, can you see why this one is so exciting? Because here you can at least store the heat. So you're not storing the sunlight, but you can store the heat, so you can use that heat to boil water to make steam to spin a turbine whenever you want. This is at least storable. You did? The one on over in Vegas? Yeah, I showed a picture of it, but you weren't here to see. What? There's a lot of names for them. They're called concentrated solar thermal.
How do they store it?
You know, the same way that insulation preserves the heat of my coffee, that stuff is at like 800, 900 degrees. So they put it in underground insulated storage, and it'll stay 800 to 900, you know, it'll stay over 200 degrees for a long time. So in the middle of the night, when Las Vegas needs to put on more lights, you can still make electricity because heat stores. Like 6 miles, 5 miles, 10 miles, 15, 20 miles, 40 miles? I don't know, how far is it? Yeah, I don't think it's that far. Question?
With the escape ones, like one using opportunity, I think you cycle that in factory instead of going.
The grid's a one-way street. You can't put stuff back. It's not like a ripple effect. Yeah, you can't like move it. Okay, number 46. ¿Quién habla español? ¿You habla español? ¿You habla? ¿Qué significa secuestrar? So what? Kidnap. Sequestration is to kidnap carbon dioxide. Yeah. Has anybody heard that carbon dioxide might cause certain problems?
I think so, only one time, bro.
One time you might have, yeah, maybe overheard that somewhere.
Yeah, I think-
You know, global warming and ocean acidification. 46 gets 2 stars because you have an article that discusses a few different ways. Please look up 1, 2, 3, 4, 5 different sources. Of sinking carbon before it gets to the atmosphere. To use artificial trees that make sugar, to make gigantic artificial algae blooms in the ocean to soak up all the CO2, to bury it under deep sea sediments, stuff it in caves, turn it into concrete. There's some concrete that uses carbon dioxide. If you don't do the homework, you're not going to get the test point. But you should know that sequestration is the process of capturing carbon dioxide, of trapping CO2 to kidnap CO2. I don't know, it's written on the whiteboard, maybe that'll help you. It wouldn't do you much good if you're just trapping it for a little while. Like if you just blow up a balloon and then you pop it, like you're just kind of playing with it. But you know, if you can take it out of the system for a geologically significant time, then yeah, absolutely. You know, all that CO2 leaked out of the biosphere over hundreds of millions of years. Remember we talked about the carbon cycle in unit number 3 or something? All that CO2 is leaked out of the atmosphere, stuck underground in biomass, in fossil fuels. And all of a sudden, we're just lighting it on fire and putting it all in the atmosphere at once. The only reason that our climate is getting bleak is we have this CO2 that's been gone for a long time that we're bringing back into play. Imagine what it would do to the economy if I just brought out all the money that's ever been printed. Same thing is true. We just have too much CO2 right now. It's more than our biome can adjust to. So if there's a way to hide that CO2, that'd be really nice. No, but if it comes back out as a trickle, you know, like if you bury it under deep sea sediment, it's not going to come out all at once in 100 years, like it did the way that we burn all the fossil fuels. If it just trickles back out to the system, that's one thing. Flooding the market with CO2, that's another. Okay, good times. Number 47, This one gets 1 star, and that's because a lot of this information was already in your book. And if you didn't understand it in the book, it might be easier to get it out of the article. '47 was previously discussed in study goal number 26. Ways to make coal-burning power plants cleaner. Bridget, would you please put away your cell phone? Number 48, I think everybody knows the pros and cons of wind power. And you'll notice that's your second pro and con question of the day. And we had a pro-con question yesterday, too. Can I get some pros of wind power? Yes? Clean, what else? Efficient, it's cost effective, what else? Relatively, we've got a lot. Plentiful, clean, cheap, renewable. Yeah, that sounds pretty good. What are the cons? It's not all the time. Birds and bats in the blender. Cost effective, it's not nearly as bad as you think.
Wind's not always right.
Yeah, it's not dependable. It doesn't always go up. It actually makes a pretty good amount of energy. Per dollar invested, it's actually a very cost efficient energy type.
Why do you do it breaking down? Is your mind really moving that fast?
They're not, but birds don't look up. Birds aren't evolved to look above them. So they always see it on the side where it's coming up at them, but they don't see it on the side where it's above them. They're relatively silent. They get it.
Wind bats.
What?
Wind bats.
Yeah, and then for the bats, it's the pressure differential. There's a pressure drop from the front to the back. So when the bats fly through, they don't get hit by them, but their lungs get pulled out of their body.
What's that called again?
Pressure drop. Pneumothorax. There's one more comment nobody's mentioned. Thanks for asking, Jack. Colton, what's the other problem? People don't like looking at them. You know, those wind turbines, for them to work well, they've got to be way up in that breeze, which means you can't hide them, you can't avoid seeing them. Yeah, the bigger they are, the better they work, so you got to put them higher in the air so you see them even more. The best places to put them is usually ridge lines, so you see them from everywhere. You can't hide them, because the place where you hide them is going to be no wind. So people get really bummed about the aesthetic issues. What? Yeah, I'm not that worried about them either, but I don't know. And by the way, a lot of this can be resolved by putting them into the water, so a lot of people are talking about coastal wind farms, but you realize that's a separate set of trade-offs now, because there's a lot of people who need coastal areas for various reasons. Okay. No, because the fish don't fly, and there are birds there, but birds don't usually spend too much time over water. So you get a few miles offshore, there's not that many birds that you can find. Right. Ocean-based, they're above the ocean surface, yeah. So fish don't. Okay, that was number 48. And I'm not going to give out any stars because we already had it in this conversation. How many of you remember that from 33? So many of you were gone in Mexico, right?
You haven't done the start today.
Thank you. Number 49, Negawatt gets 3 stars. That is number 49. Negawatt program gets 3 stars. What is it?
Unit of power that represents an amount of energy saved.
No, that would be a mega. Oh, yes, energy saved. Yes.
A unit of power that represents the amount of energy saved.
It's a unit of power that represents energy savings. Negative wattage. Megawatt. Energy savings. So negawatt programs are ways that we get people to use less energy. Like, you ever seen those stickers next to the light switch that says like rethink energy usage or something, or think before you flick the switch or whatever? Those are negawatt programs trying to encourage energy efficiency. There's a lot of ways to do that. You can give people free light bulbs. You can give them smart power strips, little stickers, efficiency checkpoints for electricity usage. And there's one truism in environmental science that even if you don't write it down for notes, I want everybody to remember. Andrew Gallagher with the cell phone.
Easy.
The one truism of environmental science that I want everybody to always remember, like for the rest of your life, just a life lesson, like take it from me, bros, you'll need this later. Energy savings is always a good idea. Anything that you can do, conservation is always better than another way to supply it. We always want to find a cheap supply, but efficiency is always better. If you're just not using the energy in the first place, you don't need any supply. The only way to be an environmental hero and have no consequences, no negatives associated, is to just use less stuff. Efficiency always wins. Why not nukes? I think we talked about yesterday, right? Y'all remember the why not nukes? Did we get to that conversation? My fear of commitment?
Yeah.
How humans can't make me the promise that they're going to protect our stuff for 100 gazillion years because humans don't last that long? Okay. So that one, number 50, gets 1 star, but it was already answered. Number 51 gets 2 stars, and we're almost done. How could ethanol be a scam? I thought it was short cycle carbon. Isn't that a good thing? You might remember when we did the car lot of the future, this came up. How could ethanol be a scam? You grow some corn, you make some alcohol, you stop using gasoline. Isn't that a good thing?
Is it worth like mileage in gas cars? So
They get worse mileage because ethanol has less energy content, and right? That's right. It takes a lot of gasoline to make the corn. You have to spend 1.2 barrels to make the ethanol that saves you 1 barrel. In economics, that's really not smart. Spend $1.20 to save $1. Coincidentally, it's also not as high quality of a fuel, right? There is one sense in which ethanol would be a perfectly brilliant plan. That 1.2 barrels to make ethanol, what type of ethanol did I just make? No, not fuel grade ethanol. What do I get the ethanol from? What am I growing with that 1.2? Corn. I've said it before and I'll say it again. Biofuels are good, but agricultural biofuels are bad.
just like you do your own time.
No, instead of using an agricultural product, if you made your ethanol with algae, which don't take a lot of energy inputs to grow, or if you used waste material, like wood chips, we have a lot of wood fiber, and you can make alcohol out of that too. The reason that we've never really gotten into that is in order to try out the system, you don't want to start with the most difficult possible problem. You kind of baby step your way, right? So to get started on ethanol, we're like, well, ethanol, baby steps. Let's take the easy ethanol, we'll use corn, because the United States makes a lot of corn. And then that started to look like it wasn't going to be that good, so we never really went much further in the development of other ethanol technologies. But there's still a few people investing in that. I think in your lifetime it'll happen. In Chile, they have like a tremendously successful giant kelp ethanol program. That's super, super good carbon savings. That's excellent. I'm done with the stars in the reading packet, but there's one thing I'd really like everyone to look at. Please take out your reading packet and look at the last page. I think this is completely, utterly, totally fascinating. Check it out. I'd like everybody to please take a second to peruse this paper, see what you're looking at. This is a chart of the ionizing radiation a person could absorb from various sources. The unit for absorbed dose is a sievert and measures the effect a dose of radiation will have on the cells of the body. 1 sievert all at once could make you sick. Too many more will kill you. We safely absorb small amounts of natural radiation all the time. Getting it all at once is worse than spreading out the timing. Now look at that. Look at that scale. If you start in the upper left, snuggling next to someone gives you a certain amount of radiation. It's not a lot, but you know, everything has a little radioactivity in it. So if you sleep close to another human, you'll get a little radiation. It's about half of what you get if you live 50 miles away from a nuclear power plant, which is slightly less than you get from eating 1 banana. Because bananas have a lot of potassium, and some amount of potassium is radioactive. Yeah.
It says like
Yeah, and you, Sawyer says airplane flight. So if you scale down a few, eating 1 banana, living within 50 miles of a coal-burning power plant gives you way more radioactivity than a nuclear one. An arm X-ray, a CRT monitor, being in a place that has higher than average radiation, like the Colorado Plateau, a dental X-ray. The background dose you receive on any average day, look, that's 10 bananas. That's just what you receive in, you know, the terms of just being a human on Earth. But look at how much you get from an airplane flight. What was your question about that, sorry? I reckon that they must, because, you know, a pilot who does this a whole bunch, they would probably rack up quite a few in their life. You realize they're closer to the sun, so they're protected by less atmosphere while they're flying. So you get more radiation because you're closer to the sun. Yeah? Okay, I'm so glad that Grant asked this question. He said, how do those 8 blocks flying from New York to LA, how does that correlate to the rest? Everybody please look up. I find this paper to be totally fascinating. I always want you to remember it. Look at me. This entire box is scaled right there. So all the doses in the chart to the left is right there. It's about 3 chest x-rays. If you start scrolling down, living in a stone brick or concrete building, the average dose for 3-mile accident for somebody who was within 10 miles. Keep on scrolling. Yearly dose from natural potassium in the body. The yearly limit of exposure to a single member of the public. Look at how much a mammogram is. My wife has to get one of those, I believe, every 6 months from now until she dies. Because I told you all she has breast cancer. Some of you might not have been here because you're in Mexico. So because my wife has breast cancer, she has to get a mammogram at least once a year, maybe once every 6 months, depending on the results of tomorrow's biopsy.
Yeah.
Is that not ironic? And so look at that, a mammogram, that's 3 microsieverts. If you compare that, look, this one right there, the top corner, second one down. The dose from spending an hour on the grounds at the Chernobyl plant in 2010 is 6 microsieverts on average. So every year my wife is spending an hour at the Chernobyl plant because she has to get 2 mammograms per year. So if she lives 40 more years, it's like spending a 40-hour session chilling at Chernobyl.
Wait, so
That would be worse at Chernobyl because she'd be getting it all at once. In her future, she'll be spreading it out over 40 years. But you know why I'm so like that? Am I the one that's getting a little nervous about that? You all see what I mean?
wait, and then that do you get some radiation?
Yeah! Assuming I slept anywhere near my wife. Bathtub. Yeah. Go back to the tub. I thought we could snuggle.
It's that much.
Because that was like, isn't that like a message? My daughter.
What?
Having a daughter. Like a girl.
No, but that's interesting.
I have two sisters.
My pilot homie just had a daughter.
And like all my dad's pilot. My dad has 3.
Wait, what?
Okay, watch this. Then you can scale all of those into these, and you can scale all of those into that, and look at how much you got for 10 minutes next to the Chernobyl reactor right after the explosion and meltdown.
Survival sometimes possible.
I mean, there's a lot of interesting conclusions that you could draw from this. One, like Cameron says, that's why nuclear power is a bad idea because that could happen. Yes, that's one. That's very scary. Meltdowns are for serious, really bad. Yeah, totally. Another interesting thing about this paper is you're always getting some radioactivity, right? Like we're just live on Earth right now. We're getting some amount. And so how does that scale to other things? When we freak out about a chest x-ray, what is that? Like living another extra couple of days? It's not that bad. Like all the x-rays I've had, I've broken ribs twice, I broke my neck, I broke my jaw, I dislocated my shoulder, broke my tailbone. So I've had like, what, maybe 40 core x-rays? That's like I've lived an extra month. That's not such a big deal. You could probably figure out how to number those. Like, I'm not going to shoot from the hip and make it up, and I don't want to take the time to read this. But the reason I like this graph is it puts those things into perspective. You can scale that down. So I just thought this would be interesting. That's why I did this. Does anybody else think that's an interesting piece of paper? Is it less confusing now that I've talked about it?
Yeah.
You'll see how they scale, those little lines that show you how the blocks compare to the different scale. So these are the little baby ones. These are like the day-to-day ones. These are like the big old lifetime ones. And this compares it to really crazy Chernobyl. Yeah. Bridget, no way you're on your cell phone again. Thanks, Summer. Summer, you do better than that. He's good. Let's stop this video.
Now?
Bye.